This is the EdExcel AS Level Further Maths Paper 2 from the October 2021 series, and in this paper we will be taking a look at the Decision 1 D1 module. Question number 1. We have a list of numbers shown here, and this list of numbers is to be sorted into descending order. For part A, we have to perform one pass of a bubble sort. Starting at the left-hand end of the list, you must write down the list that results at the end of this first pass, and with that we have to write down the number of comparisons and the number of swaps performed during this first pass. Here we have our original list of numbers. We will make a note of the number of comparisons and the number of swaps. We first of all compare the 3.5 with the 6.3. So that's one comparison. Do they need swapping? Yes, they do. So we have one swap. So 6.3 goes here. And then for a moment, let's temporarily place 3.5 here. And now we compare the 3.5 with the 2.9. So now we have two comparisons. Do they need swapping? No, they don't. So we can leave the 3.5 here. And temporarily, the 2.9 will go here. We now compare the 2.9 with the 5.4. So that's three comparisons. Do they need swapping? Yes, they do. 5.4 is larger than 2.9. So 5.4 would go here, and temporarily the 2.9 will go here. We now compare the 2.9 with the 3.1. So we have made four comparisons. Do they need swapping? Well, 3.1 is larger than 2.9, so they do indeed need swapping. So the 3.1 will go here, and temporarily the 2.9 will go here. We now compare the 2.9 with the 2.8, so we've got another comparison. Do they need swapping? No, they don't, because 2.9 is larger than 2.8. So 2.9 would stay here, and temporarily let's write down the 2.8 here. We then compare the 2.8 with the 3.7. So that's another comparison. Do they need swapping? Well, 3.7 is larger than 2.8. So 3.7 would go here, and temporarily the 2.8 will go here. So we made another swap there. Now we compare this 2.8 with the 1.7. So that's another comparison. Do they need swapping? Well, 2.8 is larger than 1.7, so they don't need swapping. So the 2.8 will go here, and temporarily we write down the 1.7 here. We then compare the 1.7 with 4.1. So that's another comparison. Do they need swapping? Well, 4.1 is larger than the 1.7, so they do need to be swapped. So 4.1 will go here, and temporarily we write down the 1.7 here. We then compare the 1.7 with the 3.3. So that's another comparison. Do they need swapping? Well, 3.3 is larger than 1.7, so they need swapping. So 3.3 will go here. And temporarily, the 1.7 will go here. We then compare the 1.7 with the 2.2. So that's another comparison. And do they need swapping? Yes, they do, because 2.2 is larger than 1.7. So the 2.2 would go here, and the 1.7 has been moved to the end of the list. So here is our first pass completed. How many comparisons do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have made 10 comparisons. How many swaps have we made? 1, 2, 3, 4, 5, 6, 7. We have made 7 swaps. For part B of the question, after a second pass using this bubble sort, the updated list is shown here. And for part B, we have to use a quick sort on this updated list to obtain the fully sorted list. You should show the result of each pass and identify your pivots clearly. Here is our list, and we have to use a quick sort. Well, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 entries. The middle entry would be the 6th entry, which would correspond to this 2.9. So we will box the 2.9, indicating this is our pivot. And everything larger than the 2.9 will go to the left of this pivot. Everything smaller will go to the right of this pivot. We need to make sure we write down the numbers in the order they appear though. We compare the 6.3 with the 2.9. 6.3 is larger, so it stays here. We compare the 5.4 with the 2.9. 5.4 is larger, so it stays here. We compare the 3.5 with the 2.9. 3.5 is larger, so it stays here. We compare the 3.1 with the 2.9. 3.1 is larger, so it stays here. We compare the 3.7 with the 2.9. 3.7 is larger. We compare the 4.1 with the 2.9. 4.1 is larger, so it goes here. 3.3 with 2.9. 3.3 is larger. 2.9 with 2.8. Well, 2.8 is smaller, so that means we write down the 2.9 here. We then need to underline it, indicating we've used it as a pivot. And then we've got the remaining entries, the 2.8, the 2.2, and the 1.7. So that's this pass complete. Now we've got 2 sublists which we need to split down the middle. In this sublist we've got 1, 2, 3, 4, 5, 6, 7 entries. The middle of those will be the 4th. The 4th entry would correspond to the 3.1. And in this sublist, the middle entry will be the 2.2. But the 2.9 will stay where it is. We don't need to do anything with this 2.9 because we've already used it as a pivot. So with this sublist, 6.3 is larger than 3.1, so 6.3 goes here. 5.4 is larger than 3.1, so 5.4 goes here. 3.5 is larger than 3.1, so 3.5 goes here. 3.7 is larger than 3.1, so 3.7 goes here. 4.1 is larger than 3.1, so 4.1 goes here. 3.3 is larger than 3.1, so the 3.3 would go here, and then we have the 3.1. We need to underline it, indicating we've used it as a pivot. What about this sublist? Well, 2.8 is larger than the 2.2, so 2.2 would stay here and the 2.8 would go here. The 1.7 is smaller than the 2.2, so 2.2 goes here and the 1.7 goes here. We need to underline the 2.2, indicating we've used it as a pivot. Now, for the next pass, well, we need to focus on this sublist here. We don't need to consider the 2.8 and the 1.7 being pivots because they are in between two entries which have already been selected as pivots. So nothing is happening with the 3.1, the 2.9 and the 2.2. So we can underline these because we've already used these as pivots, and the 2.8 will stay where it is, so will the 1.7. Now here we've got 1, 2, 3, 4, 5, 6 entries. The middle one will be either the third or fourth entry. We choose the higher one, so we choose the fourth entry. So the 3.7 is our pivot. 6.3 is larger than 3.7. 5.4 is larger than 3.7. 3.5 is smaller than 3.7. However, the 4.1 is larger than the 3.7, which means we would write the 4.1 here, the 3.7 here, and the 3.3 is smaller than the 3.7, which means we have 3.7, 3.5 and 3.3, and then we underline the 3.7, indicating we've used it as a pivot. So now we have this sublist and this sublist. Well, the middle entry will be the 5.4, and the middle entry to the right will be the 3.3. We compare the 6.3 with 5.4. 6.3 is larger. 4.1 is smaller. So the 5.4 will stay here, and the 4.1 will stay here. We underline the 5.4 indicating we've used it as a pivot. And the 3.5 is smaller. The 3.5 is larger than the 3.3, so the 3.5 would remain here, and then the 3.7 won't change. We've used it as a pivot. Then we've got the 3.3. We need to underline it, indicating we've used it as a pivot. And the rest of the entries will remain the same, as we see here. Now, we can't compare the 6.3 with anything. We can't compare the 4.1 with anything. We can't compare the 3.5 with anything. And we can't compare the 1.7 with anything. And so what you can see here is our completed quicksort. So this is our completed sort. Now, for part C, we have to apply the first fit decreasing bin packing algorithm to the fully sorted list to pack the numbers into bins of size 11.5. What's key over here is we've got a bin size of 11.5. Now, before we do anything else, what we worked out in part B was putting the original list into descending order. Now we need to use the first fit decreasing bin packing algorithm, which means we need to write down the numbers into descending order first and then apply the first fit algorithm. So, in decreasing order, here is our list of numbers, which is this final pass we got from the quicksort. Now what I have created here are three separate columns. We've got this column where we will be labeling our bins, this column what we will put into the bins, and in this column the remaining space in the bins. So we first of all open up a new bin. We'll call this bin 1. And in bin number 1, we've got space 11.5. We place the 6.3 into that bin, so we can cross off the 6.3. And then the remaining space then will be 11.5 take away 6.3, which is 5.2. If we take a look at this 5.4, we don't have enough space in bin 1, so what we need to do is open up a new bin, bin 2 say, which has space 11.5 into it. We place 5.4 into bin 2, and when we do that, the space left over, 5.4 would leave a space of 6.1. 11.5 take away 5.4 is 6.1. Let's now take a look at the 4.1. Is there enough space in bin 1? Well, yes there is. So the 4.1 would go here. And the remaining space, 5.2 take away 4.1, that's 1.1. Let's take a look at the 3.7. There's not enough space in bin 1. However, there is enough space in bin 2. So we place the 3.7 here. Let's cross it off. And the remaining space in bin 2 then, 6.1 take away 3.7, That's 2.4. Let's take a look at the 3.5. There's not enough space in bin 1. There's not enough space in bin 2. So we need to open up a new bin, bin 3. It has space 11.5. We place the 3.5 into bin 3. So if we do that, the remaining space, 11.5 take away 3.5, that's 8.0. Let's take a look at the 3.3. There's not enough space in bin 1, there's not enough space in bin 2, however there is enough space in bin 3. So 3.3 would go here. And the remaining space, 8.0 take away 3.3, that's 4.7. Let's take a look at the 3.1. There's not enough space in bin 1, there's not enough space in bin 2, however there is enough space in bin 3. So we can put the 3.1 here, which would leave a space of 1.6, and the 3.1 can be crossed off here. Let's take a look at the 2.9. There's not enough space in bin 1, there's not enough space in bin 2, there's not enough space in bin 3. So we will have to open up a new bin, bin 4, and we place the 2.9 into bin 4, which would leave a space of 8.6. We now take a look at the 2.8. There's not enough space in bin 1, there's not enough space in bin 2, and there's not enough space in bin 3, however there is enough space in bin 4. So we can place the 2.8 into bin 4, and the space remaining will be 5.8. Let's now take a look at the 2.2. There's not enough space in bin 1, however there is enough space in bin 2. So we can place the 2.2 into bin 2, and this will leave space 0.2. Now, if we take a look at the 1.7, there's not enough space in bin 1, there's not enough space in bin 2, there's not enough space in bin 3, however there is enough space in bin 4. So we can place the 1.7 into bin 4, and if we do that, the remaining space will be 4.1. We have sorted the items into 4 bins, and so 4 bins are required. For part D of the question, we have to determine whether our answer to part C uses the minimum number of bins. You must justify your answer. Well, for part D, what we need to do is first of all calculate the lower bound. And for us to calculate the lower bound, we need to add together each of these numbers and then divide by the 11.5, which is our bin size. So here is how we work out the lower bound. We add together all the various entries and then we divide by 11.5. And if we work this out, we can therefore conclude that the lower bound is equal to 3.2 391, etc. And the value we see here is less than the 4 we saw here, that 4 bins were required. And so we can conclude that our answer to part C uses the minimum number of bins. Question number 2. A project is modelled by the activity network shown in figure 1. So figure 1 here shows an activity network. The activities are represented by the arcs. The number in brackets on each arc gives the time in hours to complete the corresponding activity. The exact duration x of activity n, shown here, is unknown, but is given that x is in between 5 and 10. Each activity requires 1 worker. The project is to be completed in the shortest possible time. And for part A, you have to complete the precedence table in the answer book. Here we've got the precedence table. We've got activities A to Q, and let's just use diagram 1 to help us. Well, A, B and C rely on no other activities, so we can put a dash here for A, B and C. If we take a look at activity D, it depends on A only. So D depends on A, and if we take a look at activity E, it only depends on A. So E depends on A only. If we take a look at activity F, which is here, this relies on C only. Look at the direction of the arrows. F depends on C only. If we take a look at activity G, what goes into G will be B, E, and it will also be activity C, which is indicated by the dummy here. So activity G depends on B, C, and E. If I take a look at H, that depends on B, it depends on E, and it also depends on C, and that's indicated by the dummy. And so H would depend on B, C, and E. If I take a look at activity I, that depends on B, it depends on E, and it also depends on C, and that's indicated by the dummy. So activity I depends on B, C, and E. If I take a look at activity J, that depends on D, and it also depends on G. If I take a look at activity K, which is here, it depends on D and G. If I take a look at activity L, this depends on I, and it also depends on F. So L depends on F and I. If I take a look at activity M, this depends on I, and it also depends on F. So M depends on F and I. Activity N, well, this replies on J only. So N depends on J, And if I take a look at P, well, it depends on H, it depends on L, and because of this dummy here, it will also depend on G and D. And so P will depend on D, G, H, and L. And if I take a look at activity Q, it depends on H, it depends on L, but because of this dummy, it also relies on G and it relies on D. So Q relies on D, G, H, and L. Here is our completed precedence table. For part B, we have to complete diagram 1 in the answer book to show the early event times and the late event times. Here is diagram 1. Going into A, we have the source, which has 0 for the early event time, and then 0 plus 7 is 7. So 7 goes here. Then here we've got 0 plus 6, which is 6. So 6 goes here. And noticing that the dummy has a weight of 0, going into here, we either have 7 plus 4, which is 11, 0 plus 8, which is 8, or 6 plus 0, which is 6. The largest one is 11, so 11 goes here. Next, going into here, we have 11 plus 6, which is 17, or 7 plus 5, which is 12. The larger one is 17. 17 goes here. Going into here, we have 6 plus 7, which is 13, or we have 11 plus 8, which is 19. So 19 goes here. Now, going into here, noticing that a dummy has a weight of 0, 17 plus 0 is 17, 11 plus 4 is 15, 19 plus 10 is 29. The largest one here is 29. 29 goes here. Next, going into here, we have 17 plus 11, which is 28. Nothing else is going in, so we write down 28 here. And then into here, we either have 19 plus 6, which is 25, or we've got 29 plus 9, which is 38. The largest one is 38. Now, going into here, noticing that a dummy has a weight of 0, 38 plus 0 is 38, or we have 29 plus 5, which is 34, or we have 17 plus 16, which is 33, or we've got 28 plus x. Now we know that x is in between 5 and 10. It doesn't equal 10 and it doesn't equal 5. So the largest possible value of 28 plus x will be 28 plus 9, which is 37. So the largest one here is 38. Now for the late event time, in our sync we put in 38, and now we need to work backwards. So here, 38 take away 0 is 38, 38 goes here. Then we have 38 take away x. That's the only one for this one, so here we've got 38 minus x going in here. And we now need to work out what goes here. Well, we're at 38 so far. 38 take away 9 is 29. Or we could have 38 take away 5, which is 33. Nothing else is coming out from here, so the smaller one from these is 29. So we write down 29 here. Now, in here, we either have 38 take away 6, which is 32, or we've got 29 take away 10, which is 19. Those are the only ones coming out of here, so the smaller one is 19. If we take a look at what we could have here, we could have 38 minus x take away 11, so that will be 27 minus x. Or we could have 38 take away 16, which is 22. Or we could have 29 take away 0, which is 29. So that's another option we could have. 29. The smallest one, well, if x is in between 5 and 10, the largest value of x is 9. So 27 take away 9 is 18. So the smallest one that could go here is 27 minus x. Now, let's figure out what could go here. We could have 27 take away x take away 6, so that's 21 minus x. We could have 29 take away 4, which is 25. Or we could have 19 take away 8, which is 11. The smallest one here, well, if x can be 9 as the largest value, 21 take away 9, that's equal to 12, so the smallest one will be 11. Now, working backwards even further, 11 take away 0 is 11. 19 take away 7, that's 12. The smaller one here is 11, so 11 goes here. Here we could have 11 take away 4, which is 7. Or we could have 27 minus x minus 5, so that will be 22 minus x. Now if x is 9, the largest value it can be, 22 take away 9 is definitely bigger than 7, so 7 goes here. And now if we work backwards, 7 take away 7 is 0, 11 take away 8 is 3, 11 take away 6, that's 5, the smallest one is 3, so 3 goes here. Here is our completed diagram. For part C of the question, we have to list the critical activities. If we go back to our diagram, we are looking for where we have 0 float time. And so, for part C, when we come to find the critical activities, A has 0 float time. Then you can see A has 0 float time. You can also see that I has 0 float time. You can also see L has 0 float time, and also Q has 0 float time. So for the critical activities, we have A, we have E, we have I, we have L, and we have Q. These are our critical activities. Now, for part D, it is given that activity J can be delayed by up to 4 hours without affecting the shortest possible completion time of the project. We have to determine the value of X. You must make the numbers used in your calculation clear. So, we know that activity J can be delayed by up to 4 hours, which means the float time for activity J is equal to 4. So if we take a look at activity J, which is this activity here, we can work out the float time by working out 38 minus X minus the 11 minus the 17. The difference between these will equal flow. So for the float time, we have 38 minus X minus the 11 minus the 17. This is equal to 4, because we know that the float time is equal to 4, and if we solve for X, X is equal to 6. Now for part E, we have to draw a cascade chart for this project on grid 1 in the answer book. Now, if we take a look at our diagram, the first thing we can do is find the critical path. The critical path, we go A, then E, then I, then L, and then Q. These are the critical paths because we've got 0 float time. And so, knowing that we've got 0 float times, we can state that the critical path we have A, E, I, L, Q. This is our critical path. So now what we can do is add this critical path to our diagram here. So here I have added the critical activities A, E, I, L, Q. Now we need to add on activities B and C. We also need to show their float times. So if I take a look at activity B, the float time here, well, if we go back to the question, we have to draw a cascade chart, and we have to start off at the earliest time. So we've got 0 to 8 for B, and then we've got a float time of 3, because 8 plus 3 gives the 11. So we look at the late event time to calculate the float. The float for B will be 11 take away 8 take away 0, which is 3. If we add on the other floats whilst we're here, for C, we've got a float of 11 take away 6 take away 0, which is 5. If we take a look at D, knowing that X is equal to 4. 27 take away 4, it is rather with x equaling 6, we have 27 take away 6, which is 21. And here 38 take away 6 is 32. So if I add on this 32 here. For the float for activity D, 21 take away 5 take away 7, if I work this out, 21 take away 5 take away 7, that's equal to 9. So we've got 9 here. For activity G, we have 21 take away 6 take away 11, which is 4. For activity J, well, we know that the float here was equal to 4. We were told that in a separate part of the question. For H, we have 29 take away 4 take away 11, which is 14. F, we've got 19 take away 7 take away 6, which is 6. For M, we have 38 take away 6 take away 19, which is 13. And are we missing any others? Well, for N, we've got 6 for the weight. So if I work out the float for N, we have 38 take away 6 take away 28, which is 4. So N has a float of 4. For K, we have 38 take away 4 take away 28, which is rather 38 take away 16 take away 17, this is 5. And then for P, we have 38 take away 5 take away 29, which is 4. So with all that, we know the float times, so we can complete our cascade diagram. Here is our completed cascade diagram with the relevant floats. You can see activity D depends on A, F depends C completing, G and H depend on E completing, J and K depend on G completing, M depends on I completing, N depends on J completing, and P depends on L to complete. And then the float times are shown shaded in the bars. Question number 3. Donald plans to bake and sell cakes. The 3 types of cake that he can bake are brownies, flapjacks and muffins. Donald decides to bake 48 brownies and muffins in total. Donald decides to bake at least 5 brownies for every 3 flapjacks. At most, 40% of the cakes will be muffins. Donald has enough ingredients to bake 60 brownies, or 45 flapjacks, or 35 muffins. Donald plans to sell each brownie for £1.50, each flapjack for £1, and each muffin for £1.25. He wants to maximise the total income from selling the cakes. If we let X represent the number of brownies, Y represent the number of flapjacks, and Z represent the number of muffins that Donald will bake, we have to formulate this as a linear programming problem in X and Y only, stating the objective function and listing the constraints as simplified inequalities with integer coefficients. You should not attempt to solve this problem. Well, we want to maximize profit, so the first thing we will write is we want to maximize P. Now, in this question, we sell each brownie for £1.50, each flapjack for £1 and each muffin for £1.25. So we want to maximize P equals 150 x plus y plus 1.25 z. And we want to maximize this objective function subject to the following conditions. Now if I go back to the question, we've got 48 brownies and muffins in total. Brownies is x, muffins is z. So the first thing we have is x plus z equals 48. Next, we have to bake at least 5 brownies for every 3 flapjacks. So the next inequality we've got is 3x being greater at equal to, because we've got at least, and then we have 5y. And then at most 40% of the cakes will be muffins. Now 40% is the same as 2/5 as a fraction. Now the total muffins is given by x plus y plus z. And we want at least 40%, so we've got 2/5, lots of this. And we want at most 40% of the cakes to be muffins. Muffins, remember, is z. So all this must be greater or equal to z. What else we know is, if we go back to the question, we've got enough ingredients to bake 60 brownies, 45 flapjacks or 35 muffins. Now, if we have one quantity of the whole ingredients, we want to use 1/60th of those ingredients on brownies, 1/45th on flapjacks, and 1/35th on muffins. And so we have x over 60 plus y over 45 plus z over 35. Now, if we go back to the question, we have enough ingredients to make this many brownies, this many flapjacks, and this many muffins. So this must be less than or equal to 1, where 1 is the whole quantity of ingredients. So we've got these constraints, and if we go back to the question, we need to solve our linear programming problem in x and y only. So what we can do here is simplify each of these. So how could we go about this? Well, let's first of all label all of these. We've labelled all our constraints with our objective function. Now if I take a look at what I have for equation 2, I want to get rid of the z because the question said formulate this linear programming as a linear programming problem in x and y only. So I need to eliminate the z. So from 2 I can eliminate the z. Z equals 48 minus x. I'll call this equation 6. So now that I know what equation 6 is, well, let's just leave that alone for a moment. Let's simplify equation 4. From equation 4, if I multiply through by 5 and then expand the 2 into the bracket, I've got 2x plus 2y plus 2z being greater or equal to 5z. And if I subtract 2z from both sides, we've got 2x plus 2y being greater or equal to 3z. I'll call this equation 7. Now if I take a look at equation 5, we can also simplify that. So from equation 5, well, if I write everything over a common denominator, what would our common denominator be? 60 times 45 times 35. We get 94500. And from that, how many x's will we have? Well, we'd have 45 times 35 x's. So if I take that out as a common factor, we've got 1575x. In terms of how many y's we'd have 60 times 35 y's, which is 2100 y's. And in terms of z's, we've got 60 times 45 of those, which is 2700. And this is less than or equal to, well, what I'll do here is I'll multiply through by this value here. So I've got 94500. And that's if I get rid of this. So this is what we can conclude from equation 5. Let's call this equation 8. And I'm not going to simplify anything right now. We'll just leave that alone. Well, could we actually simplify? Well, it looks like I can divide each of these terms by 75. And if I do that, 1575 divided by 75 is 21. 2100 divided by 75, that's 28. And then 2700 divided by 75, that's 36z. And then 94500 divided by 75, that's 1260. So I can't simplify this any further. What I'll do is I'll call this equation 8 instead. So I need to substitute equation 6 into everything that involves a z. So if I substitute 6 into 1, well, I know that equation 1 is p equals 1.5x plus y plus 1.25z. Now I know what z is, that's 48. Take away x. So if I tidy all of this up, what do I get? I get p equals, well, how many x's do I have? I've got 1.5 minus 1.25. So I end up with 0.25x. How many y's do I have? Well, I'll just have one y. And how many constant terms do I have? 1.25 times 48. I have 60 constant terms. So I'm going to call this equation 9. So this is our objective function, by the way. Now if I take a look at equation 7, I can substitute 6 into 7. So if I substitute equation 6 into equation 7, I've got 2x plus 2y being greater or equal to 3z. Now I know what z is, that's 48 minus x. So if I tidy up this, well, I'm going to have a minus 3x on the right hand side, and if I add that over to the left hand side, I'm going to have a 5x, and then the 2y, and this is going to be greater or equal to 3 times 48, which is 144. Let's call this equation 10. Now, if I substitute equation 6 into equation 8, I've got 21x plus 28y plus 36z. Now z is 48 minus x. This is going to be less than or equal to 1260. So 21 minus 36, I have minus 15 x's, and then I have 28 y's. And if I do 36 times 48, and then if I do 1260 take away this, I get minus 468. And if I rearrange this inequality, we've got 15x being greater or equal to 28y plus 468. So let's call this equation 11. So with all that, we now have enough information to state our required solution. So we want to maximize p equals 0.25x plus y plus 60, subject to 3x plus 5y, 3x being greater or equal to 5y, 5x plus 2y being greater than 144, and 15x being greater or equal to 28y plus 468. Here is our solution. We have formulated a linear programming. The problem as a linear programming problem. Question number 4. Dijkstra's algorithm has been applied to the network in figure 2. A working value has only been replaced at the node if the new working value is smaller, and that's standard by Dijkstra's algorithm. For part A, we have to state the length of the shortest path from A to G. So, from A to G, which is over here, the shortest path, well, that's going to be 66. So, for part A, that quite clearly is 66. Now for part B, we have to complete the table in the answer book giving the weight of each arc listed. We have to note that CE and arc EF are not in the table. So, from A to B, we start off with 0 and then 25 goes here, and that's the only thing here, so that suggests to us 25 must have been the weight. And then from here we have 37, and we also have 35. Now if I take a look at the 25, if I were to add 10 to it, I would get the 35. So somewhere here I got 37, presumably by having 0 plus 37, but that was replaced by going from B to C directly. And here, from 0 to give the 45, I must have had 45, but then it was replaced, I got 42 in the end. From 35 to 42, I have 7. Now, what else could we figure out from here? Well, what we'll do is we'll add in the arcs as we're going along. So AB, that's going to be 25. A to C, that's going to be 37. Then AD, so from A to D, that's 45. Then BC, going from B to C, that's 10, we discussed that. Then BE, going from B to E, well, from B to E, we're at 25, we want to get to 56. So 56 take away 25, that's 31, so that means 31 must have gone here. So let's add on 31. CD, so starting at C, going to D, well, we discussed that was 7. CF, we are at C, we want to get to F, so we've got 63 here. We started at 35, so 63 take away 35 is 28. So 28 goes here. And then CG, so that's here to here. Well, if you think about it, we're at 35, and then to get the 74, which was the first value shown, 74 take away the 35 gives 39. So we've got 39. So let's add that on. We've got 39. And then we also have CE. Well, if we go back to the question, we know that CE is not in the table and EF is not in the table, which suggests to me that we don't know the weight of this arc and we don't know the weight of this arc. Let's just put a question mark here, and let's put a question mark here. We don't know what those are yet. What else can we figure out? Well, how do I go from D, which is here, to G? Well, I'm at 42, and then I improve that to get this 70. So 70 take away 42 is 28. So I've got 28 over here. Then I've got EG after that. So I'm at E, I want to get to G. Well, I've already got the 70 here, and to improve this further I get 68. I'm at 56, I want to get to 68. So 68 take away 56 is 12. So that means 12 goes here, which is also shown here. And then FG, so I'm at F, I want to get to G. Well, I improve the 68 to get 66. I'm at 63 already. To get to 66, I need 3. So 3 goes here. So I've completed this table as follows. Now for part C, we have to state the shortest path from A to G. So from A to G, the shortest path, we have A to B, and then we've got, after the 25, the next smallest one is this 35. So that's next. So we've got AB, then BC. Then after this, the next smallest one out of the going to F. And the reason for that is because we want to get to the 63 and then add the 3 to get the 66. If I went to D first and then G, this would have given me the 42, and then the 42 would have added, I would have added on the 28 to that to get the 70, so that's not the shortest path. So that's why I have to go to F. And then when I'm at F, I can go straight to G to get the 66. And so for part C, the shortest path will be given by A, B, C, F, G. Here is the shortest path. Now, for part D of the question, it's now given that when Prim's algorithm is applied, we start from A, and the order in which the vertices are added to the tree is AB, BC, CD, CE, EF, and FG. The weight of the corresponding minimum spanning tree is 80, and the shortest path from A to F via E has weight 67. And we have to determine the weight of the arcs CE. Now CE is what we said over here. So CE is this arc here, and the arc EF, these are what we are trying to find out. So we start off with AB, and AB has weight 25. So for part D we have AB, and then after that we've got BC and CD. So then we've got BC and then CD. After that we've got CEEF. So we've got CE, and then we've got EF and FG. So this is the order in which we're selecting everything in. AB, I know that AB, if I go back to my table here, AB is 25. So I've got 25. BC, well, what we'll do is we'll tick as we're going along. So I've got AB, and then I've got BC. Now BC, is that in the table? Yes it is. It's 10. I've got 10 here. CD, that's 7. So I have 7 here. CE, do I know what that is? Well, I don't, but CE, I put in a question mark here. So then I've got the CE, don't know that. And I don't know the weight of EF either. But then FG, I know FG is 3. If I use the others, I wouldn't get a minimum spanning tree. So here I add on 3. And if I add all these together, I know I get 80. Now, what we can conclude from here then is CE plus EF, this will equal 80 take away 3 take away 7, which is 70, take away another 10, that's 60, take away 25, so that's 35. Call this equation 1. And from the question, I also know that the shortest path from A to F via E has weight 67. So A to F via E has weight 67. So how could I get there? Well, I need to go and select everything in the shortest possible way. I'm definitely going to go E to F. What's the shortest way that I can get this 56? Well, to get this 56, I did 25 plus 31. So that means I must have gone through B, and here I must go through A because the shortest path from A to B is 25. It's the only way I can get the 25. So the next thing we can say is the shortest path from A to F via E, we're going to have A, B, E, F. So that's how we get that path, we've just discussed it. So A to B, and then B to E, that's going to be 56. So we've got 56. And then we're going to add on EF. And the result of this is 67. We were told that in the question. We'll call this equation 2. Well, let's just put an inequality, therefore sign here. So now if I solve these, what we can therefore conclude from equation 1 and 2, well, we can conclude EF will equal 67 minus 56, which is 11. And then if this is 11, CE will equal 35 minus 11, which is 24. So CE is equal to 24. I have found the value of CE and the value of EF. So whilst we're at it, well, we don't need to add those to our diagram, we'll just leave it as it is. Here is our final answer. And that would conclude the end of this paper.